Okay, good morning. Today, what I'm going to do is I'm going to continue the discussion of the quantum mechanics part of this chapter. We started that yesterday, and then today's Wednesday, so we may start getting into the electron configurations tomorrow. If we don't do it tomorrow, we'll do it on Tuesday. Okay. So what we said was that the electron, or even an atom, but we're going to focus primarily on the electron, that we can think of as a particle. It has electric charge, it has mass, right? So it has electric charge. It has mass. Okay. One question that comes up is, does it have size? Is there a size? And it turns out that's a complicated question about the size of an electron. There is a way to calculate a size, but it turns out that that is an incorrect calculation. And so the size is it's a little tricky. So what we know about it is that now it can behave as a particle under some conditions, but it can also behave as a wave under other conditions. And so we call this wave-particle duality. And since the electron is the primary particle that's responsible for chemical bonding, right, in chemical reactions, essentially, because of that, the wave-like properties of the electron are important to us. We have to consider them when we start talking about how chemical reactions are occurring at the microscopic level. So what we said was there was this de Broglie wavelength that we could calculate, and that was equal to a constant, Planck's constant, right, divided by the momentum of the particle that's in motion, or the wave that's in motion, right? And so this was 6.626 times 10 to the negative 34 joules times seconds over the momentum, which is the mass of the particle times its speed, or technically it's its velocity, but we can just go ahead and use its raw speed. Okay. Now, what I want to do before we get into the ramifications of this is I want to talk a little bit about the Heisenberg uncertainty principle. Okay. Werner Heisenberg came up with this idea, which is essentially says there are certain fundamental limits to how well we can make measurements. If you recall what I said about this matter wave, right? It's a matter wave. The electron has mass, so it's matter, but it's also a wave. Is that it turns out there are limits to what we can know about these matter waves. And the one that I'm going to focus on, there's certain combinations of limits, but the one I'm going to focus on is the relationship between momentum, which is mv, right, and position, which we'll call x. Okay, momentum and position. So imagine that you have a particle and it's sitting along the x-axis. So it's right here. Okay, so let's just, for cartoonish perspective, imagine that's our electron's little particle just sitting there on the x-axis. Okay, and let's imagine that we want to be able to observe that electron. We want to be able to look at it, right? Electron is too small to see with your eye, for sure, right? Even excellent eyesight is not good enough. In fact, can't see an electron even with a light microscope. So what do? You have to use some kind of technique. So what we might do, which is very clever, is use something that's analogous to visible light, but has a shorter wavelength. It turns out the wavelength of the light you're using determines how much resolution you have, how small you can see things, you can resolve things. So if you want to look at a star, you might use a telescope, but you can use your eyeball, right? You can look at the stars with your eyes. You don't really need anything special. You're using visible light. And then, but if you look at something a little smaller, like you want to see a planet around, a planet like, I don't know, Uranus or Neptune, you need a telescope, right? So you need to start focusing the light, right? But you're still using visible light to do that. Well, it turns out you can reach a limit and you just can't see stuff with visible light. You just can't really make a microscope and that can, or a telescope or a microscope that can actually resolve the fine details. And it turns out that the limit has to do with the wavelength of the light. Because remember, the wavelength is essentially a measure of the size of the wave, right? So if I have something that's this big, you want to use a wave that is smaller than that size. So this is kind of right at the limit, right? If you think about it, here's the wavelength. There's your wavelength. That wavelength is pretty close to the size of the object you're trying to look at. So that would be kind of a limit. We sometimes refer to it as the diffraction limit, right? But if you're trying to find something that's like this big, you can't use this wave. This wave, the wavelength is so much larger than the size of the particle, it's just not going to work for you. So what do? You move to a shorter wavelength, right? Remember, shorter wavelength is higher frequency. So suppose I say, well, even that's no good. Even that wavelength's 2. So what I'm going to do is I'm going to use a wave that has a really, really short wavelength, right? Now your wavelength is that thick, and that's about the size of the particle. So maybe you could start to actually like look at this thing, So that's essentially the issue. So let me erase this. What Heisenberg noticed is that if we do a thought experiment on this and start thinking about what's going on, imagine this particle is moving, and we're just to simplify it, it's just moving in the x direction. It might be moving that way, it might be moving in that way, but it's moving, right? So if it's moving, it has a changing position, right? Its position is changing, so x is changing. It also is moving, so it has a speed, it has a velocity. Change in position over change in time is velocity. So for that reason, it also has a velocity. And notice momentum has velocity in it, right? So there's position x and velocity v. Now here's the thought experiment. We want to figure out how fast it's moving and where it is. Sounds like a reasonable thing to do, right? Like if you're looking at an airplane, you see, oh, there it is, and you kind of measure how fast it's moving, or a car or a person that's running, right? We do that with races, right? If people are racing, whether they're running or driving, you figure out how fast they're moving and use a speedometer for that and all that kind of stuff, right? Radar guns, actually. So here's how you would do it. It's a small particle, right? An electron is a subatomic particle. So the way you would do it is you would have some sort of source of radiation. So I'll just do a little light bulb. That's our source of radiation. And that radiation, these waves are going to bounce off. And then they're going to come off the electron and go into like a detector. I'll draw a little eyeball to represent the detector, right? And then what do? You do a calculation. You say, okay, at this time it's here. At that time it's there. The difference in positions divided by the amount of time, right? So you got to measure position and time, right? So velocity is the change in the position, delta x, over the change in time, delta t. Well, here's the problem. The problem, according to Heisenberg, was that if you want to be able to see this electron, you want to be able to measure it, right? Not see, but measure. You have to use a wavelength that is able to resolve where this electron is. So it's got to be about the size of the electron, right? That's that diffraction limit. So you can't use visible light, you can't use ultraviolet. Turns out you got to use like X-rays. And here's the problem with using X-rays. And remember that the energy of a photon is equal to hc over lambda. In other words, if you're using an X-ray, lambda is very, very small. Like 10 to the negative 10 meters. That's a really short wavelength, right? But the smaller this is, the smaller the wavelength is, the greater the energy is of that photon. So what happens is you're sending these X-rays they're going to move the electron. They're going to change its position. And if you change its position, you're also changing its velocity, by the way, right? So you have this conundrum. You want to measure what it is, where it is, and how fast it's moving. So you use shorter and shorter wavelengths, but the shorter and shorter wavelengths have greater and greater energies, which move the particle away from where it initially was. So you're changing it. So what this says is an observation issue. If you want to observe something, you actually have to change it. We normally might have thought, oh, you just look at it, right? Well, just looking at it is changing it. Now, normally, if it's something macroscopic, looking at it changes it so little we don't notice and we can ignore that. But if you're talking about an atomic particle or a subatomic particle like an electron, just the act of observing it changes it, okay? And so that puts a limit in terms of how well we can know the position and the velocity of the electrons. So why is this an issue? Well, the nucleus of the atom has electrons around it, right? So, okay, even if you use de Broglie, right? De Broglie said it's a wave. Even if that's the case, maybe we want to know kind of where the electron is in that atom and how fast it's moving, you know. What the Heisenberg Uncertainty principle says is, sorry, you can't do that really. Because what happens is if you want to study, if you want to observe that electron's motion, you will have to use such short wavelengths, X-rays essentially, that the energy is transferred to the electron will change its behavior. So you don't ever get to observe what it's doing. You can to some extent. The problem we'll look at will show how bad you can, how badly you can, but you're limited. And that's called the Heisenberg Uncertainty principle, okay? So what I'm going to do is I'm going to set up, to some extent, the equation. So again, this is Heisenberg's formula. This is not a course where we'll go through how he got it, but I want to introduce this idea. This is X's we're going to use for position, okay? So imagine this is the X-axis. So it's right here, right? So we'll say this is X1. That's its initial position, right? In fact, we'll use an I. We'll use I and F, initial, final, like we've been doing before. Then you could say, well, imagine I don't know exactly where it is. Imagine that I think it's somewhere in this range here. Okay, right there. Right, that's what you're talking about is uncertainty. It's somewhere in there, but I don't know exactly where. So this is what we call delta X, which is called the uncertainty. And that's where this idea, the uncertainty principle, that's why it's called the uncertainty principle. What we're saying is we cannot claim the electron is right here, but we can claim that it's somewhere in this range. Heisenberg didn't say we can't know anything about the electron. He just said there were limits, right? And the calculations and the experimentation shows that that's the case. Now, imagine that it's moving, right? So it's moving. This particle, not only does it have a position and uncertainty in position, it's actually moving with a velocity, okay? So essentially, you have the same thing. You can say, hey, there's an initial velocity, but there's also an uncertainty in the velocity, delta V. So imagine it this way. If you said, hey, how fast is that car moving? You might say, okay, it's moving 50 miles an hour. Or you might say, well, I'm not sure. It's going anywhere from 45 to 55. Or it's going anywhere from 40 to 60. I knew it was going fast, so maybe it was going 40 to 60 or 60 to 70. That's an uncertainty, right? You're saying there's limits to what you can know. So I'm going to put those two ideas together, this uncertainty, and we're going to write it this way. If you take the uncertainty in the position and you multiply it by, I'll put this in parentheses, mass times uncertainty in velocity, that product, multiplying all three of those together, has got to be, according to the Heisenberg uncertainty principle, greater than h over 4 pi. I won't go through where the 4 pi comes from, but you do recognize h, right? H is this Planck's constant. Okay, 4 pi is in there as well. And remember, mv, m times v, is equal to momentum, linear momentum, right? We said if an object is moving in a line, it has linear momentum. So really what this is called is uncertainty in momentum. So I'm going to write it this way. This is the way you'll see it. Delta x times delta p is greater than or equal to, sometimes you see it over this way, h over 2 with a line through there. If you're doing Google searches and you're doing Wikipedia search and all that kind of stuff, you may see it that way. H bar over 2 is the same as h over 4 pi. Okay, it's just a symbol that we use. Okay, now this is not as useful for us because the mass of the particle is not going to change. We're going to assume that's constant. So let's just say delta x times m times delta v, right? And so there we go. So this is the formula. There's two forms of it. The top one is the one that we'll use for our calculations. It's a little more direct, but the bottom one is sort of the famous representation of the Heisenberg uncertainty principle. Okay. And there it is. Okay, so uncertainty. So what does it say? It says that the uncertainty in the position times the uncertainty in the velocity times the mass is greater than or equal to this number, which is h divided by 4 pi, which is just a number, right? You can just calculate that as a number. So this side over here is just a number. It's a constant. H over 4 pi. H is a constant, 2 is a constant, pi is a constant. This is the mass of the particle. Notice there's no kind of wave calculation here. We're not calculating anything about waves. So Heisenberg was actually looking at this as a particle. There's your uncertainty in the velocity. There's your uncertainty in the position. And typically what they want you to do is to calculate one of those two. You know the mass of an electron, mass of an atom. These are constants. They'll tell you the uncertainty in the position of one of them, and then you find the uncertainty in the position, or the uncertainty in the other one. So you may know the uncertainty in the position and want to find the uncertainty in the velocity. So let's take a look. Now, and the problem you're going to do is actually it has typically units as an issue as well. So let's come over here and look at this problem. Okay, finding the minimum uncertainty, right, in the position or velocity. Just as I said, you're going to find one or the other. An atom of krypton. So this is not an electron here. This is an atom. We're looking at the uncertainty in the position and velocity of an atom. Okay, but they are small, so you can still do it. It has a radius of 88 picometers, 88 pm, and an average speed in the gas phase of 172 meters per second. Remember, we could do that calculation, right? If we know the temperature of a gas, we can figure out what its average speed is. We could do that from chapter 10. Square root of 3 RT over molar mass, right? We could do that. But they're telling it to you right there. Suppose the speed of the atom at 25 has been measured to within 0.10%. Okay, so there's the key. That's telling you the uncertainty in the velocity, right? The speed is velocity within, that's a range within some percentage, right? 1% of 100 is 1, 1% of 10 is 0.1. So that's essentially telling you as a percentage what the uncertainty in the velocity is. Calculate the smallest possible length of a box, uncertainty in position, the atom could fit with certainty. And then they want you to just kind of go through and do this as a sort of like ratios. They want you to represent it as the number of ratio, the ratio of this uncertainty in position divided by the size, which was right here, 88 picometers. Okay, so we'll go through. That's just a detail of how you present the answer. So let me stop share here. Bring this up, and I'm going to write the the information that we really need here to do this calculation. Okay, put this right here. First of all, we're talking about an atom. And they're telling us the size, the radius. It's very common with atoms to give the radius, not the diameter. Not sure why. Well, there's a reason why. It has to do with how we measure things. Okay, so there's the radius of this particular atom. It's a krypton atom, right? So we know it's krypton. Okay. And we know that the velocity is 172 meters per second. And then they tell us that the speed is known within 0.10%. Okay, now find the minimum size of a box, okay, the atom could fit in. Okay, so here's what you're doing. You're saying, look, we have some measure of the uncertainty. I'll go through the calculation on that. This is delta V. This is going to give us delta V. So what do you calculate at? You calculate delta X, right? So what we're saying is you got this atom, it's going to be in a box. And the box, the size of that box is delta X. Okay, so you're going to calculate delta X to see how much uncertainty in the position we have. So like, suppose delta X ends up being, you know, really small. Suppose it's this big. Then essentially we know how big the atom is, right? But if the box is this big, then that means we don't really know how big the atom is. Okay, that's sort of the idea. Now, it turns out there are ways to measure sizes of things, and that's what that 88 picometers is there for. Okay, so let me show you how we go about this. So I'm going to write delta X times M times delta V. So I took the parentheses out there. And just set it equal to, because we're trying to find the minimum size. So the minimum size would be equal to H over 4 pi. Okay. Now, one thing we don't know, it's not given, is the mass of a krypton atom. We don't know that. We can look it up, but be very careful, because when you look up the mass of an element like krypton, the units for an atom of that element are in atomic mass units. So when we look up krypton, the atomic mass of krypton is 83.80. You could do grams per mole, but that's if you have a mole of atoms. We only have one atom, so make it AMU. So that's the mass of one atom. Okay. So those are not MKS units. We want to use MKS units just like we've been doing. So here's what we do. We use our conversion factor. 1 AMU is approximately 1.661 times 10 to the minus 27 kilograms. That's the conversion factor between AMU and kilograms. So if I multiply this by 1.661 times 10 to the minus 27 kilograms over an AMU, you're going to get some very small number, right? 83.80 times 1.661 times 10 to the minus 27, and you get 1.392 times 10 to the minus 25, and then your AMUs are gone and you got kilograms. Okay, so there's your mass in kilograms. We need to use MKS for all of this. All right. Okay, so now we have M, and we, in a sense, we have delta V. We just don't have it like in the correct numerical value. So here's how you deal with this. This velocity is in the MKS system, 172 meters per second, but that's not the uncertainty. That's just the measurement. We think it's going 172. That's actually calculated. It's not measured, it's calculated. It's calculated via that square root of 3RT over molar mass. How good is that calculation? Well, it's within 0.1%. So what that means is plus or minus 0.1% of this value. That's what that means. So 0.1% of 172 meters per second, and meaning it could be more than 172, it could be less than 172, anywhere in that range. Now, 0.1% is pretty good, right? Like if you measure something to 0.1%, you're doing okay. That's a pretty decent calculation. I mean, a pretty decent measurement. So let's write it this way. How do we calculate 0.1% of 172, right? So we want 0.1% of 172. Well, that would be 0.1 over 100. A percent is divided by 100 times 172, right? That's the calculation, 0.1% of 172 times 172. Well, that's easy enough. That's 0.172. Okay, so really what we're saying then is the uncertainty in the velocity is 0.172 meters per second. That's really what that's saying. Okay, so now we know delta V. So what can you calculate? Delta X. Very simple. So let's take this equation here. If we want to know delta X, we're going to have to divide both sides by mass. So we're going to put mass down here, and we're going to have to divide by delta V. So we're going to put delta V down here as well. So your uncertainty in position is going to be equal to h over 4 pi. But now we're going to multiply it by m and delta V. Okay. And then you just put all those numbers in. It should work out MKS because we've got everything in meters and seconds and kilograms and all of that. I'm going to go ahead and show you how the remember I did this yesterday with the de Broglie equation. But remember, h is 6.626 times 10 to the negative 34 joule seconds. But remember, a joule is a kilogram meters squared per second squared. So keep that in mind in terms of the dimensional analysis. So h is 6.626 times 10 to the negative 34 kilogram meters squared per second squared. But that's a joule, but it's a joule second. Remember, h is a joule second, so joule second. And then you divide that by 4 pi. Okay, well, pi is unitless. I'm going to put a bunch of sig figs there. And then you've got your 1.392 times 10 to the negative 25 kilograms. And now we have our uncertainty in position, 0.172 meters per second. Okay, so what happens? Well, the kilograms cancel. This second cancels with one of those, right? So actually the h constant is really kilogram meter squared per second because the seconds cancel. And then you've got your meters here. One of those cancels with that one. And then you got another second here that cancels. So you're going to just end up with meters, right? Your answer will be meters. Okay. All right. So delta X is going to be, now you got to do this funky calculation, right? So 6.626 times 10 to the minus 34 divided by 4 divided by, I have a pi symbol in here. I do. I'm going to divide it by pi divided by 1.392 times 10 minus 25 divided by 0.172. Okay. Oh man, it came out with a funky number on my calculator. It drives me crazy when it does this. What it does is it puts all these zeros and then has one digit at the end. Now, what you do is you just move the decimal 2, 4, 6, 8, 9 until you get to the last digit. So it's really 2 times 10 to the minus 9, but we need more significant digits, right? So I'm going to multiply it by 1,000. And then it's 2202. So it's 2.202 times 10 to the minus 9 meters. Okay. So there's your uncertainty in the position. What that means is, according to the Heisenberg uncertainty principle, which appears to be very powerful, perhaps unbreakable rule of the universe, a law of the universe, is that if we measure the velocity of the atom to that uncertainty, and it has that mass, the best we can know the position is with this amount of error, which seems pretty good, right? It's a pretty small number. But the problem is this is even smaller. This is smaller than this number here. May not be obvious why. So let me show you how it is. What they ask you to do is to calculate this uncertainty as a ratio of the size of the atom, of the radius of the atom, right? So the radius of this krypton is 88 picometers. Okay, well, what I'm going to do is I'm going to put that into meters. So this would be 88. What's a pico? 10 to the minus 12. So 88 times 10 to the minus 12 meters, right? I just substituted 10 to the minus 12 for pico. That's a simple way to do it. That's in meters now. So now let's do the uncertainty in the position. It's 2.202 times 10 to the minus 9 meters, right? So there's our, so they're both in meters. So now you can do a ratio. So the ratio is you take delta X over the radius of your krypton. They said to do it, I'll show you why it works out this way. So you take your delta X, 2.202 times 10 to the minus 9 meters, and then divide that by the radius, 88 times 10 to the minus 12 meters. See how that 10 to the minus 9 is bigger? It's a larger number. 10 to the minus 9 is larger than 10 to the minus 12. So 2.202 times 10 to the minus 9 divided by 88 times 10 to the minus 12, and you get 25.02. But they say just round it to a whole number. Like, is it twice as big? 2. Is it 3 times as big? 3. Is it 4 times as big? 4. So delta X over the radius of the krypton atom is going to be equal to 25. Now, what does that mean? That means that the uncertainty is 25 times the radius of the atom. So what's 25 times? Well, if this is the atom here, the radius is half of that. 25 times would be like this, I guess, you know, about like that, right? This is about 25 times the radius. Okay, so if we measure the uncertainty and the velocity to 0.172 meters per second, 0.1% of 172, okay, that's what you're going to end up with. You're going to end up with an uncertainty in the position that is 25 times the radius of the atom. Okay, so you want to say, okay, what's the diameter? The diameter is 2 radii, so it's 12.5 times the size, the diameter of the atom. It's very, very large uncertainty. And this is not some kind of experimental problem in terms of, oh, you just need a better machine or better technique. It's actually a fundamental limit of nature. Just as you've heard that you can't go faster than the speed of light, right? Can't take a starship and go faster than the speed of light because of the fundamental speed limit, the speed of light. Same thing here. You can't measure something with more precision or smaller uncertainty than is given by this particular equation. And there are other relationships too. There's one between uncertainty and energy and uncertainty and time. There's angular momentum as well, that kind of thing. So there you go. All right. So for most people, the equation is pretty simple, right? I mean, the numbers are funky in terms of the magnitudes, but most people have a problem with the percentages. So if I say 1% of 500, what you do is you take 1 out of 100, right? Percent is out of 100 times your 500, and that would be 5. So if I have 0.01% of, I don't know, let's make 750, okay? You would take 0.01 over 100 and then multiply that by 750, okay? So that'll give you like 0.0750. Okay, so that's that one issue. And then the other issue that people have will, represent it as a multiple of the radius. So what you do is you take your uncertainty in the position divide that by the radius, that's going to give you a number that you round to a whole number. They don't want fractions, they just want a whole number. So you round it. And what that says is, just mathematically, if I multiply both sides by radius, I get 25 times the radius of the krypton, right? So by taking this ratio of uncertainty in position over the radius that's given, multiply both sides by the radius, you get this. And this says that the uncertainty in the position is 25 times larger than the radius of the atom. And there you go. So there's really, in a sense, only two ways these problems can go. They can give you the uncertainty in the velocity, or they can give you the uncertainty in the position, and you just calculate the other one as some ratio. Okay, so there you go. So the reason we go through that is that there's a couple of reasons. One is it puts it into context. This idea that we're going to, that we're going to be able to take the atom and say, hey, here's the electron, there it is, we see it, it'd be nice, we want it, I remember when I was taking general chemistry and I was kind of doing my own calculations, like, oh man, I want to know what's that electron doing, where is it, how fast is it going? It does have a speed, it has a velocity, and it has a position, but the uncertainty in those quantities are dependent on your measurement, and that's also kind of funky aspect of it too. We're not going to go into that really. It's an amazing aspect of quantum mechanics. The act of measurement, though, changes the object. And so if you're not measuring it, you don't know, right? If you don't measure something, you don't know about it. Is it actually change? Like, what's happening when you're not measuring? And so all we can say is that the act of measuring a subatomic particle, or even a particle, an atomic particle like a krypton atom, changes that particular particle. Okay, so that's the Heisenberg uncertainty principle. What I want to do now is I want to start talking about the next section, which is atomic orbitals. Okay, so I'm sorry, let me come over here. And so this is going to be section 6.6. Which is called quantum numbers. Okay, 6.6. Okay, so the idea here comes out of the work of Niels Bohr. And we remember the Bohr model, Heisenberg, and Schrodinger. So these are the three. I mean, I'm not, claiming these are the only people, but these are the three big people that worked on this together. They actually worked sort of as a team, some independent and some together. Bohr was the boss, and Heisenberg and Schrodinger. Well, actually, Heisenberg was a student. These were all Europeans working in the 1915 to 1930 or so, before World War II. And they came out with some really kind of amazing breakthroughs. So essentially, what Schrodinger said, and as chemists, we focus mainly on Schrodinger's work, less on Heisenberg because of the mathematics. Chemists are not real good at matrix algebra in general. Heisenberg's work was matrix algebra. So if you take linear algebra, if you're taking that as an engineering major, you'll see that's a weakness of chemists in general. Schrodinger used differential equations. And these differential equations, chemists were more likely to kind of pick that up. There's also a physical intuition that comes out of the Schrodinger approach, but all together is called the Copenhagen interpretation, because they were working in Copenhagen. So it's called the Copenhagen interpretation of quantum mechanics. And that's essentially what we're going to use, is the Copenhagen interpretation of quantum mechanics. There are other interpretations. You maybe have heard of the many worlds theory, that anytime a measurement is made, the universe splits into two. So there's an infinite number of universes that are being created or that exist. But there's very little evidence for that, if any. and it's just kind of thinking. So the Copenhagen interpretation seems like a pretty decent, it works. It works for chemistry, it works for physics, it works for engineering. So we're going to use that Copenhagen interpretation. So essentially the Copenhagen interpretation says that as you get to smaller and smaller scales, particles behave more and more differently than they do in the regular world, right? So that value of h is essentially what determines it. H is a very small value, the Planck constant. Because it's small, small particles behave as quantum particles and large particles behave as classical particles, okay? There are limits to what we can know. That's the Heisenberg uncertainty principle. When we're talking about quantum particles, we have to give up the idea of knowing the position exactly and the velocity exactly. What we do instead is we talk about essentially waves, okay? So it's also referred to as the wave interpretation. And so the Schrodinger equation says that every electron, we're focusing on electrons now, okay? Each electron has a function, a wave equation it's called. And this wave equation is a function of position, x, y, z, three-dimensional space, and time, okay? The next thing we will say is it turns out that this wave equation in its straight form there is as psi, this is psi, right here, the symbol psi, has actually very little use for us in terms of as scientists making measurements. What's more useful is the square of it. So if we take the square of this function, sorry, and we square it, this gives us the intensity of a wave. Notice it's not, I got rid of the equal sign, I'm just doing proportional to. It's giving us, in a sense, the intensity of the wave, which we are going to interpret as the probability of the wave at a particular spot position in space, not spot, position in space. So we don't need to go through the whole mathematics, it's beyond the scope of this course, but the point is, if we can somehow figure out what this psi squared is for the electron, it's going to tell us not where the electron is, but what the probability of the electron is, the probability that it is in some spot. So the way this is typically shown is you have a nucleus, right? There's our nucleus. The nucleus is tiny, it's pretty localized. But the electron, we're going to say, hey, we're going to calculate probabilities. And what we'll find is there's a very large probability that the electron is close to the nucleus. So I'm going to draw lots of dots. I'm drawing like hundreds of dots in there around the nucleus. The electron is somewhere around there, most likely. There's a high probability that it's there. Okay, so I shade that in pretty darkly. Then as you move further away, the probability becomes smaller. Now this kind of makes sense, right? The electron is negatively charged, the nucleus is positively charged, so the electron should be pretty close to the nucleus. It makes sense, right? Why would it be far away? And so quantum mechanics actually kind of confirms that there's a high probability it's close to the nucleus and lower. So notice I'm drawing fewer, more widely spaced. So this is lower probability. And then in here is higher probability. Okay, that kind of makes sense, right? Now, am I breaking any rules, the Heisenberg Uncertainty principle? No, I'm not saying it's anywhere in particular. I'm just saying there's a probability distribution. So it really gets down to statistics, right? And that psi function is really, it ends up being a statistical type of calculation. So now imagine I want to represent it graphically instead of as a diagram. So on the x-axis, I'm going to put distance from the nucleus. Right? We're talking about an electron, just one electron. How far from the nucleus is the electron? Well, we can only talk about probabilities, right? So we can't say it's here, but we can say there's some probability that it's here. Probability, right? Big word. And essentially you get something that looks like this. It's an exponential decay. For those of you who don't know about exponential decay. It just falls off as you get further from the nucleus. So very high probability when you're close to the nucleus, and then very low probability as you're further away from the nucleus. Now, mathematically, an exponential decay may not cross the x-axis, right? So it may never actually reach zero. And it turns out that quantum mechanical particles have the ability to move from one position to another that you might not think is possible, okay? So there you go. There's your exponential decay. And this is a way of showing it right here. And then you can do, based on the mass of the electron, the mass of the nucleus, the charge of the electron, the charge of the nucleus, you can use what's called these wave equations. You covered in the second semester of physics, the classical wave equation, and then the quantum mechanical wave equation you cover as a sophomore level course. What you can do is you can start saying, hey, what kinds of waves do we end up with? And what kind of probability distributions are likely to occur? And these are called hydrogen-like orbitals. Atomic orbitals. Okay. These are just the ones that we get out of our calculations. And it turns out they measure out pretty well. They're pretty close. Okay. So here are the hydrogen-like atomic orbital distributions. I'm going to draw them a little differently, because drawing in all those little dots is, you know, you need an artist to do it well, right? You need an artist to do it well, and at some point it becomes kind of not very useful. So here's what we end up with. We end up with orbitals. Again, the nucleus, from now on, I'm going to draw the nucleus at the center. You end up with an orbital that looks kind of like a sphere. It looks like a sphere. And this little, instead of drawing all the little dots, I'm going to call this the 90% probability. I guess you could call it surface. Right? So what we're doing is we're saying, hey, you know, it's an exponential, so it's going to take forever to draw this. It goes out infinitely far away from the nucleus. So let's just stop at 90%, because most of the probabilities near the nucleus will stop at 90% and just draw a line to represent 90% and ignore the 10%. Reasonable thing to do. Okay. So we end up with this shape right here. It's a sphere. And we're going to call that an s orbital. Now, the word orbital comes from orbit, right? It's essentially a nod to earlier physics, the idea that you have an orbit, that the electron's orbiting. We're saying it's not, though. It's not. It's a space. This is the space that 90% probability the electron is in that space. It's a wave occupying that space. It's undergoing some kind of vibration that we don't need to worry about what the nature of that vibration is. It's a standing wave. But you can also kind of think of it as the particle is somewhere in that box, in that, or that little sphere, 90% probability that it's in there, okay? And we'll represent that. That's called an s orbital. The second type is a little bit more complicated looking. The nucleus, again, is at the center. That's going to be sort of our notation as we put the nucleus as a little dot at the center. And then we end up with these, what are called lobes, like an earlobe. And these are often drawn in different ways. Okay, I didn't draw that very well. Let me try this one again. Like I said, you sometimes need an artist to do this stuff, or at least someone who's practiced drawing. I am doing this on an iPad, so maybe it's not so easy. Okay. Notice it's got two regions of space. Again, that's your 90% probability surface. And we're going to call this a p orbital. For those of you that have taken biology, like, you know, you probably heard those terms, SPDF, right? This is where it's coming from. If you had high school chemistry, you heard it as well. So I will point out that we have something in here called a node, a nodal plane. Remember, these are three-dimensional. I'm drawing them as like little little circles, but they're actually three-dimensional. This is called a nodal plane. Okay. And the nodal plane, 0% probability. Meaning the electron has 0% probability that it's in that plane. So this is kind of cool. These are sometimes called dumbbells. People call them dumbbells. They're also referred to as lobes. That's the more common. We call them lobes. Okay. And the p orbital is, one of its properties is that it has two lobes, right? Okay. The third type is what's called a d orbital. So I'll write the name down here. Okay. Again, the nucleus is at the center and it has four lobes. So I'm going to try to draw those in. If you study lasers, okay, let me quit talking and draw these in. Two nodal planes here. Okay, so those are nodal planes. Again, they're three-dimensional. And then this right here is your 90% probability. We're ignoring the 100%. So the way that I think of these is imagine them kind of like a balloon and the surface is vibrating in and out. Like imagine there was like waves in it. Essentially, this s, p, and d orbitals are waves that are vibrating. The electron is a wave, right? It's this wave that's spread out over these regions. It's a very different way of looking at matter. And our evidence suggests that this is what actually happens. So, you know, for the p orbital, there's two regions of space that are vibrating. So for me, like I remember taking general chemistry, the question I had was, how does the electron get from one lobe to another? Like if it's moving around, how does it get from here to here? And our answer is it doesn't. Because it can't go through the nodal plane, right? Zero probability, right? It wouldn't be able to go through there. It has zero chance that it could be in that plane. So what's happening is it's not acting like a little particle that's going from one to the other. It's acting like a wave that's vibrates, spread out over both. And these are waves that you're maybe not familiar with, right? We don't tend to have these kinds of wave discussions until you get up to college level chemistry, college level physics. That's when you start to see these kind of strange things, right? It's a vibration. The electric charge is vibrating. Actually, I shouldn't say the electric charge is vibrating. The electron has electric charge, but the electron itself is vibrating. The nature of the vibrations, we don't need to worry about that. The important thing for us in chemistry is that there's geometry here. There are, you know, locations, right? So in the p orbital, the electron's not over here and it's not over here. It's somewhere in here and somewhere in here. That's going to be important when we talk about chemical bonding. Okay. Same thing with this d orbital. We don't talk much about d orbitals. This is where the electron is, in this region of space here, these four regions of space simultaneously, right? It's a complicated vibration. That's where it is. So that's going to lead us into chemical bonding because electrons are important in chemical bonding. Okay. I'm going to show you one more, and that's the f orbital. And we won't talk much about the f orbital, but I do want to show it to you. Again, here's the nucleus. And it has 6 lobes. So it's more complicated wave. There's the nucleus, right? It's got 3 nodal planes. Let's see if I can figure out where they are. I'm kind of struggling here. Let me try this again. The F orbital is not easy for me to draw. Let's put this nucleus here. I'm going to draw the orbitals. I'm going to draw the lobes a little bit smaller. So there you can see there's a nodal plane through there. And then there's a nodal plane through there. And then there's a nodal plane through there. Okay, so you got 3 nodal planes. Okay, 0 probability, right? And then this is, this whole thing, all 6 of these lobes, this is your 90% probability. Surface, right? 90% probability from the nucleus up to that surface. 10% beyond, but we ignore the 10%. Okay, SPDF. So you want to memorize that. SPDF. Okay, 2 lobes, 4 lobes, 6 lobes, right? Okay, number of nodal planes. 1, 2, 3. Okay, now it's actually a little more, the nodal planes are a little more complicated than that, but that's fine. Now, that's an introduction to what these vibrations, what these orbitals, hydrogen-like orbitals, they're calculated for hydrogen. What I want to do is I want to show you some aspects of these orbitals. So how do we characterize these orbitals? We're just going to call them orbitals for now, but they're really hydrogen-like atomic orbitals. The first thing we do is we can talk about their energy. Each orbital, if it has an electron in it, has an energy. And the energy is given by n. And notice what I'm doing here. I'm drawing in integer values, counting numbers up to infinity. Okay? The energy of the electron in an orbital is given by the value of n. What does that mean? Well, remind ourselves about Bohr. Bohr had these n values, 1, 2, 3, 4, 5, which were the energy values. Same thing here. And this is, in a sense, Bohr's model was correct about energy. He was right about energy that is quantized. Okay? So here's what we mean by that. You can have a orbital that's low in energy. So I'm going to call this a 1s. 1 meaning n equals 1. And the S is telling you the shape. It's an S shape, right? We just went over SPDF, right? But you can also have a larger orbital. The electron could be, on average, further away from the nucleus. We'll call this a 2s. N is equal to 2. This is your shape. Same shape, right? It's just bigger, has more energy. Energy is increasing in this direction. Okay, what about 3? Well, same idea, it just gets bigger. Now, again, it's a little bit more detailed than this. There's some nuances to this. It turns out that every time you go up a value of n, you get an extra node. So this one has 0 nodes. This one has 1 node, and this one has 2 nodes. Okay, so the number of nodes is equal to n minus 1. So if this is a 3s. So if n equals 3, 3 minus 1 is 2. So this one has 2 nodes. Now, what does that mean to say they have nodes? There's actually within, it's like an onion, within this wave, you have 2 nodal planes. Oh, these are actually nodal surfaces. Okay, there's 2 of them right there. Okay, for this one, there's only 1. And then for this one, there's none. There are no nodes, okay? N minus 1, 1 minus 1 is 0. So there's 0 nodes, okay? So this is called a quantum number. It's called the principal, AL, principal, like the principal of a school or principal of a company, principal quantum number. Bohr actually kind of figured it out in a sense using particle dynamics, okay? So that's N. It gives you the energy, and that's the important thing. It's the energy. That's something we can measure. We know how to measure energy. Our phones measure energy. Second to second, your phone is measuring energy. That little battery thing, right? It's measuring the amount of energy you have. So we can do that. So that means quantum mechanics actually out of that gives us something we can measure, which is the energy. Now, why is it 1, 2, 3, 4, 5, 6? It is, that's just actually the mathematics of waves. It turns out standing waves have these modes of vibration, modes, M-O-D-E-S, not node, but modes of vibration. And so when you play a guitar, you pluck the string, there is a fundamental frequency of vibration, and that sounds like something to our ears, right? And then there are what we call overtones, which are double the frequency, 2F, triple the frequency, 3F. We are also sensitive to those higher frequencies, but less. They tend to be less powerful than the fundamental frequency, right? These are essentially overtones. It's an analogous. These are overtones to the fundamental frequency. Okay, so it comes out of the mechanics, the calculations of physics calculations you would do with waves. Okay, so that's the principal quantum number. I'm out of time today, so what we'll do tomorrow is we will work on all of the notation. It's all notation, to be honest with you. We're going to count electrons. We're going to look at possibilities for quantum numbers. There's going to be 4 quantum numbers that we need to know by the end. We start with 3 and then we add a 4th to it. But this is the first one. It's called the principal quantum number. It gives us the energy. And again, notice there's an analogy. Bohr's model had n equals 1, 2, 3, 4, and those were the energies. So it actually is consistent with this quantum mechanics. Okay. Have a great day.